Good morning. Today we're going to walk through some common stumbling blocks for Unit 1 Kinematics from the AP Physics 1 curriculum.
Flippin' Physics!
This video is a free portion of my AP Physics 1 Ultimate Review Packet. If you are studying the AP Physics 1 curriculum this year, I absolutely recommend you get my full AP Physics 1 Ultimate Review Packet. It'll help you understand all of this stuff. Link is, of course, in the video description. All right, the first stumbling block is that an object with a negative acceleration can be increasing its speed. It is for this very reason that I try very hard to avoid using the term deceleration.
I thought deceleration meant to slow down.
I thought deceleration meant a negative acceleration.
I think that is probably why Mr. P tries not to use the term deceleration.
Yeah.
Right. We instead refer to acceleration as either positive or negative, which brings us to the fact that an object which is moving in a negative direction, which has a negative acceleration, will have a negative velocity, which is becoming more negative. This means the magnitude of its instantaneous velocity is increasing, and therefore its instantaneous speed is increasing. In other words, an object with a negative acceleration can have an instantaneous speed which is increasing.
What?
Yeah. Don't worry. I will clarify that soon. And my next stumbling block is that the terms instantaneous and average are often misunderstood. Bobby, what do instantaneous and average mean?
Instantaneous means at an instant or a specific time, and average means over a time period.
Right, so an instantaneous value is always at a specific time, and an average value is always over a time duration.
That is what I just said.
Yeah.
Right. And realize an object with an average velocity of 0 can have a non-zero instantaneous velocity for most of its motion.
Oh.
Okay, you know what? Let's look at some graphs of the motion of a single object. These are the graphs of the position as a function of time, velocity as a function of time, and acceleration as a function of time for the motion of an object. Bo, what is the acceleration of the object from 0 to 2 seconds?
Well, the line on the acceleration versus time graph is horizontal at negative 10 meters per second squared. So it looks like it is always negative 10 meters per second squared.
And is that an instantaneous or average acceleration?
You asked for the acceleration from 0 to 2 seconds, and that is a time duration, so the acceleration from 0 to 2 seconds is an average acceleration.
But the acceleration at 1 second is also negative 10 meters per second squared.
And the acceleration at 1.5 seconds is also negative 10 meters per second squared.
Right.
Exactly. It turns out, in this particular case, that the average acceleration from 0 to 2 seconds has the same value as the instantaneous acceleration at every point from 0 to 2 seconds. That is because the acceleration is constant in this example.
That makes sense.
Okay.
Sure.
Bobby, what is the velocity of the object from 0 to 2 seconds?
Well, the velocity from 0 to 2 seconds is over a time period, so that is average velocity. And average velocity equals change in position over change in time. So from 0 to 2 seconds, that equals the position at 2 seconds minus the position at 0 seconds, all over the time at 2 seconds minus the time at 0 seconds. And from the position versus time graph, you get 0 meters minus 0 meters all over 2 seconds minus 0 seconds. And that equals 0 meters over 2 seconds, or 0. The average velocity from 0 to 2 seconds is 0. Actually, you can tell from the position versus time graph that the object starts and ends at the same position, 0 meters, so the displacement is 0, so the average velocity is 0. That makes sense.
Right. So notice the object's instantaneous velocity is positive for every instant between 0 and 1 second. You can see that on the velocity versus time graph because the line at every point between 0 and 1 second is above the horizontal axis. And you could see that because the slope of the position versus time graph curve is positive at every point between 0 and 1 second. The instantaneous velocity of the object is 0 at 1 second. You can see that on the velocity versus time graph because the line passes through the horizontal axis and at 1 second, and the horizontal axis represents 0 velocity. And you can see that because the slope of the position versus time graph curve is horizontal and 0 at 1 second. And the object's instantaneous velocity at every instant between 1 and 2 seconds is negative. You can see that on the velocity versus time graph because the line at every point between 1 and 2 seconds is below the horizontal axis. And you can see that because the slope of the position versus time graph curve is negative at every point between 1 and 2 seconds. So, this is an example of an object with an average velocity of 0, which has a non-zero instantaneous velocity for most of its motion. But what about its instantaneous speed, you ask?
I do not think anybody asked.
The instantaneous speed of the object is decreasing from 0 to 1 second and increasing from 1 to 2 seconds.
Wait, what?
Good question. Instantaneous speed is the magnitude of instantaneous velocity. From 0 to 1 second, the instantaneous velocity goes from 10 to 0 meters per second. So the instantaneous speed goes from 10 to 0 meters per second. And from 1 to 2 seconds, the instantaneous velocity goes from 0 to negative 10 meters per second. So the instantaneous speed goes from 0 to 10 meters per second. The instantaneous speed decreases from 0 to 1 second. It's slowing down. And the instantaneous speed increases from 1 to 2 seconds. It is speeding up. Right. It's probably good at this point to identify that these graphs could represent an object in free fall, which is thrown upward with a velocity of 10 meters per second and caught 2 seconds later at the same height.
Now I can see that it is slowing down during the first half of the motion while it is moving upward, and speeding up during the second half of the motion while it is moving downward. That makes more sense.
And this is an example of what you were talking about before when you said an object which is moving in a negative direction, which has a negative acceleration, will have a negative velocity, which is becoming more negative. This means the magnitude of its instantaneous velocity is increasing, and therefore its instantaneous speed is increasing. That is what is happening in the second half of the motion. That is how an object with a negative acceleration can be increasing its speed.
Oh, right.
Right. And here is a portion of a video of mine where I demonstrate that if the velocity and acceleration of an object are in the same direction, the object is speeding up. And if the velocity and acceleration of the object are in opposite directions, the object is slowing down. I've put a link in the description below in case you want to see that full video. Okay, I do want to take a moment and point out that you have to be careful to notice where the horizontal axes are on graphs. In these 3 graphs, the horizontal axis is in 3 different locations. So yeah, be careful to notice where the horizontal axis is, so you know where the value of 0 is for the vertical axis. Okay, class. What is the slope of a position versus time graph?
Velocity.
Correct. Billy, please determine the slope and therefore velocity of the position versus time graph at 0 seconds.
Certainly. All we need to do is draw a tangent line to the curve at 0 seconds and hold up. We know it is 10 meters per second because that is the velocity of the object at 0 seconds. We can see that in the graph of velocity versus time, right?
Absolutely, that is great. But now can you please use that tangent line method you were going to use to determine the slope and therefore velocity of the position versus time curve at 0.5 seconds?
Okay, we draw a tangent line to the curve at 0.5 seconds, and we pick 2 points on the line to determine the slope of that line. Let's pick the first point to be 0 seconds, and it looks like roughly 1.2 meters. And let's pick the second point to be roughly 0.75 seconds and 5 meters. Slope, and therefore velocity, equals change in position over change in time. That is the position at the second point minus the position at the first point, all over the time at the second point minus the time at the first point. So that is 5 meters minus 1.2 meters, all over 0.75 seconds minus 0 seconds, or 5.06 repeating, which rounds to, let's use 2 sig figs, 5.1 meters per second. Oh, and that is very close to the 5 meters per second, which we can see when we read the velocity at 0.5 seconds off of the velocity versus time graph. Cool!
Well done, Billy. And hopefully you can see that the slope of the position versus time graph, and therefore velocity of the object at 1 second is 0 meters per second. At 1.5 seconds is negative 5 meters per second, and at 2 seconds is negative 10 meters per second.
Mr. P,
Yes, Bobby?
how is this going over stumbling blocks? I thought we were going to get a list or something like that.
Yeah.
Okay, right. I can see that. However, that's not really how I do things. I find that providing you with examples that help you understand the stumbling blocks is much better than just giving you a list. For example, if I draw a line on the position versus time graph which connects the position of the object at 0 seconds to the position of the object at 2 seconds, Bobby, what is the slope of that line?
Well, that is a horizontal line, and the slope of a horizontal line is 0.
And what does the slope of that line represent?
Velocity.
Right, but what kind of velocity?
Average velocity. It's average velocity.
Oh, right. We already determined that the average velocity from 0 to 2 seconds of this object is 0, but your point is that you can represent that by drawing a line through the position at 0 seconds to the position at 2 seconds and determine the slope of that line.
And all of the velocities we determined before at 0, 0.5, 1, 1.5, and 2 seconds are all instantaneous velocities.
So the slope of a line tangent to the curve is an instantaneous value, and the slope of a line which connects 2 points on the curve is an average value.
Yeah, because an instantaneous value is at a specific point in time, and the slope of a tangent line is the slope of the curve at a specific point in time on the curve. And an average value is over a time period, and the slope of a line which connects 2 points on the curve is from one point in time to another point in time, or over a time period.
And that is a stumbling block which I helped you stumble into.
Nice.
Yeah, good job, Mr. P.
Class, what is the slope of a velocity versus time graph?
Acceleration.
Bless you.
Thanks. So this is an object experiencing a constant acceleration of negative 10 meters per second squared.
It is uniformly accelerated motion, and that means we can use the uniformly accelerated motion equations, which are also called the kinematics equations.
Oh, right. These graphs could represent the motion of an object in free fall here on planet Earth, with an acceleration in the y direction of negative 10 meters per second squared.
That is absolutely correct. These graphs could represent an object which was thrown with an initial velocity of 10 meters per second upward and then caught 2 seconds later at the same height. I would definitely make sure you are familiar with these graphs. Variations on these graphs come up rather often on the AP Physics exams. Actually, I already have a common freefall pitfalls video where I walk through common freefall stumbling blocks, so I'm not going to go through that now. Feel free to use the link in the description if you want to see that. Okay, class. What is the area under an acceleration versus time curve?
Change in velocity.
Bo, please determine the change in velocity of the object from 0 to 2 seconds.
Sure. The area under the acceleration versus time curve from 0 to 2 seconds equals the change in velocity from 0 to 2 seconds. The shape of that area is a rectangle, and the area of a rectangle equals width times height. So 2 seconds times negative 10 meters per second squared, and that equals negative 20 meters per second. And that confirms what we see on the velocity versus time graph. The velocity at 2 seconds is negative 10 meters per second, and the velocity at 0 seconds is 10 meters per second. So the change in velocity is negative 10 meters per second minus 10 meters per second, or negative 20 meters per second. Yeah, that makes sense.
And class, what is the area under a velocity versus time curve equal to?
Change in position.
Displacement.
They are the same thing.
Yeah.
Yep.
Billy, please determine the area under the line at the velocity versus time graph to get the displacement of the object from 0 to 2 seconds.
Absolutely. The area from 0 to 2 seconds equals the displacement from 0 to 2 seconds, and that equals, well, let's put the area into area 1 in red, the first triangle, and area 2 in yellow, the second triangle. Each of those equals 1/2 base times height with their respective subscripts, and that equals 1/2 times 1 second times 10 meters per second plus 1/2 times 1 second times negative 10 meters per second. And that equals 5 meters plus negative 5 meters, or 0 meters. And that makes sense because we already determined the displacement of the object from 0 to 2 seconds was 0. Yep.
Thanks. Now notice a curved line on a position versus time graph means the velocity of the object is changing. That means the object is accelerating. That's what we see in these graphs. And a horizontal line on an acceleration versus time graph means the acceleration of the object is constant. Again, that is what we see for the motion of this object. But now, let's move on to look at some other graphs. Bobby, what does it mean for the motion of the object if there is a horizontal line on a velocity versus time graph?
A horizontal line on a velocity versus time graph means the velocity of the object is constant.
Yeah. And Bo, what does it mean for the motion of the object if there is a horizontal line on a position versus time graph?
A horizontal line on a position versus time graph means the position of the object is constant, so that means the object is not moving.
Yes. And Billy, what does it mean for the motion of the object if there is a straight, non-horizontal line on a position versus time graph?
A straight, non-horizontal line on a position versus time graph means the velocity of the object is constant and non-zero.
Correct. And Bobby, what does it mean for the motion of the object if there is a straight, non-horizontal line on a velocity versus time graph?
A straight, non-horizontal line on a velocity versus time graph means the acceleration of the object is constant and non-zero.
Exactly. Now, a different topic. Unfortunately, positive and negative directions are often confusing. Class, up, north, and to the right are, according to convention, considered to be positive or negative.
Positive.
And class, down, south, and to the left are conventionally
Negative.
correct. Now, I suggest you almost always use this convention. And if you ever do not use this convention, please make sure it is very clear in your solution which directions are positive and which directions are negative. Let's walk through a typical example where forgetting that down is negative can cause issues. Bobby, please read the problem, and Billy, please translate.
What is the velocity of a ball after it is dropped from rest and it has fallen 5.0 meters? Use the acceleration due to gravity equals 10 meters per second squared.
The known values are initial velocity in the y direction equals 0 because it is released from rest. The acceleration of the ball in the y direction equals negative 10 meters per second squared because in free fall, the acceleration of an object equals the negative of the acceleration due to gravity. The displacement in the y direction equals negative 5.0 meters because the ball moves down 5.0 meters and down is negative. And we are solving for the final velocity of the ball in the y direction, so that equals question mark.
Right. However, my point here was I wanted y'all to see what happens if you forget to include the negative on the displacement in the y direction.
Oh, right.
So let's make the displacement in the y direction equal to 5.0 meters, and Bo, please solve the problem.
Sure. We can use the uniformly accelerated motion equation. Velocity final in the y direction squared equals velocity initial in the y direction squared plus 2 times the acceleration in the y direction times displacement in the y direction. Substituting in the numbers gives us 0 squared plus 2 times negative 10 times 5, which equals negative 100. So the final velocity in the y direction equals the square root of negative 100. Okay, I get it. If you forgot the negative on the displacement, you get the square root of a negative number, which only yields imaginary numbers, and we should not do that in physics. So we need to remember to use negative 5 meters for the displacement in the y direction, and that means the final velocity equals the square root of positive 100, not negative 100. So the final velocity of the object in the y direction equals 10 meters per second. That's not so hard. What?
You have to be smarter than your calculator.
I am my own calculator.
Your calculator only gives you the positive solution when you take the square root of a number. You have to remember that the answer your calculator gives you could be positive or negative.
And in this case, we know it is negative because we know the ball is moving down and the downward direction is negative.
Yeah.
Right. I can remember that.
Please do. And notice that this example we just walked through the math for can be represented by the second half of the graphs for free fall we were looking at before. The initial velocity in the y direction at the top of the path is 0. The acceleration of the ball is a constant negative 10 meters per second squared. The displacement of the ball in the y direction is negative 5 meters, and the final velocity in the y direction of the ball after it has fallen those 5 meters is negative 10 meters per second. Being able to translate between representations of events like this is critical to your understanding of physics, and is even one of the question types on the AP Physics exams.
Translation between representations.
Exactly. And one last thing. Please realize you can only use the uniformly accelerated motion or kinematics equations when the acceleration of the object is constant. If the acceleration of the object is not constant, you must find another way to solve the problem.
When is the acceleration not constant?
Yeah, and what other ways are possible?
Well, one good example is that the spring force changes depending on distance from equilibrium position, so the spring force typically causes non-uniform acceleration. And you can often use energy considerations to solve problems with springs in them because they utilize the elastic potential energy equation. And if the object is moving in simple harmonic motion, then you can use simple harmonic motion equations.
But I have not learned those yet.
Right, but you will. Thank you very much for learning with me today. I enjoyed learning with you.